Stoke's theorem, what does it tell us? Let S be an oriented piecewise smooth surface. Smooth surface that is bounded by a simple closed and piecewise smooth boundary curve like C. Smooth boundary curve like C. Suppose it has a positive orientation as well. Positive orientation. Suppose you have a vector field, let F be a vector field with continuous components. Very good. Partial derivatives. Components. Then you have the following scenario. The line integral f dot dr over c can be written as double integral curl f dot ds over s. So you can convert a line integral into double integral, or you can convert a double integral into a line integral. So let's go over one example. We'll see what do we have here. In this example, I ask you to evaluate the following line integral. Evaluate line integral f dot dr over curve C, where f is actually equal to negative y squared, x and z squared, and C is curve C is the curve of intersection. Is the curve of intersection of the plane y plus z equals to 2 and the cylinder. X squared plus y squared equals to 1. Well, I want to find the line integral, am I right? We just learned something new. Let us apply this double integral. What I actually need, I need to find the curl of f first. So let us compute the curl of f. Curl of f is equal to, as you remember, Nabla operator plus f, right? So here we have to do a little bit of computation. Here we have I, j, and k, partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z, negative y squared, x, and z squared, which is equal to I, partial derivative with respect to y is 0. Partial derivative with respect to z is 0, minus j, partial derivative with respect to x is 0, partial derivative with respect to z is 0, plus k, Here, partial derivative with respect to x is 1. Partial derivative with respect to y is negative 2y. So we get plus 2y. This is my curve, all right? So my line integral f dot dr is nothing but the double integral of 0, 0, and 1 plus 2y dot ds. Okay, so here for dot ds, we call that, here you have the scenario that we have here. For C, since the region that we have here, x squared plus y squared equals to 1 and y plus z is equal to 2, you have a cross section between them, right? So here, if you have your x, if you have your y, and if you have your z here, and you have a cylinder, and you have a cross section between the cylinder and this plane. For this plane, you have y plus z equals to 2. So suppose it's just cutting this cylinder this way. And then there is an intersection between them, which is your curve C. Your curve C is just down here, for example. This is your C. Perfect. So this is what you're looking at, the intersection here. And it's positive orientation. So take a look at this object here. Here you have x squared plus y squared. So just take a look at these two. X squared plus y squared equals to 1. And if you just look at this to the object, it's just x squared plus y squared less than equals to 1. Very good. So remember that what we did before, we said that, hey, we can define z as a function of x and y. In this case, z is equal to 2 minus y, right? So finally, you can take this object dot ds, as you saw before, this becomes the double integral of just 1 plus 2y dA dot ds. The way that we define ds and then doing the dot product between these two just result in 1 plus 2y dA. Well, here you can use, for example, converting to polar form. You can say that x is r cosine theta, y is r sine theta, and this side becomes integral 0 to 1, 0 to 2 pi, or 0 to 2 pi, 0 to 1, 1 plus 2 r sine theta, and here you have r dr d theta, or you can switch between these two. That's not important, and eventually do the computation either way. You can distribute r into parentheses, 0 to 2 pi, and here you have 0 to 1, r plus 2 r squared sine theta, dr d theta. This guy becomes integral 0 to 2 pi, and you have a half r squared plus 2/3 r cubed sine theta, 0 to 1 d theta on the right. So this guy becomes integral 0 to 2 pi, a half plus 2/3 sine theta d theta, which becomes theta divided by 2. And then here you have 2/3 sine, which is going to be 2/3 cosine theta, and minus 0 to 2 pi. So if you simplify this, it's going to become 0. So you have 2 pi divided by 2, which is equal to just pi. Very good. So we were able to compute this line integral using the Stoke's theorem.